Welcome! Welcome back to the course on plasma physics and applications to fusion energy, astrophysics and industry. In this first module on plasma astrophysics, we will deal with the most powerful source of energy in our solar system, the Sun. Today, we will answer some fundamental questions about our Sun. What powers the Sun? How does it shine? We will address this question in a simplified way by using the fundamental tools of plasma physics that you have learned so far. Let me introduce first a few properties of the Sun. The solar distance from Earth is called the astronomical unit. It is approximately 1.5 on average, 10 to the 11 meters. The astronomical unit is a basic unit in the solar system and even beyond. The mass of the Sun, which is approximately 10 to the 30 kilograms, is a typical value for a normal star, and a normal star is an object that shines steadily for a fair long time by burning hydrogen. The Sun radius, which is approximately 10 to the 8 meters, is the radius of the visible disk, which, notice, is almost perfectly round. The diameter of the Sun is a little bit more than half a degree as we see it from Earth. Note that the shape of the Sun is extremely sharply defined because almost all the light we receive on Earth originate in a thin layer which is a few hundred kilometers thick, the photosphere. In fact, if we move from the center of the Sun going outwards, the matter changes rapidly from being almost completely opaque to almost completely transparent in the photosphere. The Sun emits electromagnetic radiation, and its luminosity is approximately 3.84 10 to the 26 watts. Using the famous E equal mc squared relation, this yields a mass loss of about 10 to the 9 kilograms per second, which results in a negligible perturbation to the total mass of the Sun. And finally, the elemental abundances of the Sun are typical for cosmic sources. The Sun is made approximately in mass by 73.4% of hydrogen, 25% of helium, and then 1.6% of everything else, mostly metals. The Sun is a main sequence star. That is a star that has been shining steadily for a fair amount of time. The largest mass observed for a main sequence star is of the order of approximately 100 times the mass of our Sun, while the lower limit is slightly below 0.1 times the mass of our Sun. An interesting property of main sequence star is that they follow well-defined empirical laws. One such a law is shown in this plot here, where the star luminosity is shown as a function of the star mass. This is a logarithmic plot, and we are using normalized units, where the mass of the star is normalized by the mass of our Sun, and the luminosity normalized by its luminosity. In fact, this red dot here in the middle of the plot indicate the position of our Sun. If we now try to interpolate this data with a straight line, we observe an interesting properties of main sequence star. The luminosity of the star is related to the mass of the star through a scaling law, where the exponent alpha varies between 3 and 4. This is telling us that the luminosity of the star increases much faster than the mass of the star. Let's see an important consequence of this scaling law. Let's consider a star of 10 solar masses. This means that this star has 10 times the fuel available, since the fuel is proportional to the mass of the star. However, by using the scaling law and assuming an exponent alpha equal to 3, we obtain that the luminosity of the star will be 1,000 times the luminosity of our Sun. This means that this star will burn its fuel 1,000 times much faster than our Sun, and therefore it will live 1000 times shorter. In the following, we will derive these fundamental properties from basic principles. We know from everyday experience that a cloud of gas tends to fill all available space. On cosmic scale, this is not true because of the gravitation that tends to contract the gas under its own weight, heating it up eventually to a temperature which is high enough to ignite nuclear fusion. An equilibrium is reached when the gravitation force, which acts to contract the star, and the gas pressure force acting to expand the star are balanced. This is the so-called hydrostatic equilibrium, and in a nutshell, the Sun is a gravitationally self-confined nuclear fusion reactor. What we're going to do next is derive the hydrostatic equilibrium equation and compute the central temperature of the Sun. Now, to start deriving the equation for the hydrostatic equilibrium, let's make a first hypothesis. That is, the Sun is a perfectly spherical object. The radius of this sphere is the Sun radius, which is 7·10⁸ meter. Let's then consider a spherical shell which is located at a distance small r from the center of the Sun, and this shell has a radial thickness dr. Let's then indicate with the ρ the local density of the matter inside the shell, and with the mr the total mass inside the spherical shell. We can write down the force balance in the following way, where the first term describes the acceleration forces, the second term describes the gravitational forces, and g is the gravitational constant in SI units, and the third term describes the pressure forces. P is the pressure inside the Sun. Let's now make the second hypothesis by assuming that the acceleration can be neglected, since the Sun has been in equilibrium for a very long time, and therefore we assume an hydrostatic equilibrium by dropping the first term in this equation. In doing this, we're balancing the pressure forces that tends to expand the matter inside the Sun with the gravitational forces that tends to contract the mass of the Sun under its own weight. Let us now multiply by 4 pi r cubed and integrate by parts between the center of the Sun and r0, which is the radius of the Sun. Let's now consider only the left-hand side of this equation. And let's integrate by parts. We can easily observe that the first term goes to 0, since the pressure at r0, it is assumed equal to 0. Therefore, we're left with the following expression, which we can write in the following way, where we have defined an average pressure where V is now the total volume of the Sun. Now, if we go back to the hydrostatic equilibrium equation and we plug what we just found into this equation, we end up with the following, where the right-hand side member represents the gravitational energy of the Sun. Now, in order to compute the average pressure P, let's make a further hypothesis. We assume that the volume in the Sun is filled with a plasma which is made out of n protons and n electrons at the temperature T, and we will then use the equation of state of an ideal gas. We can thus write the average pressure in the following way, where Kb is the Boltzmann constant. Let's make the following approximation, that the mass density is a constant, and we can therefore write in the following form, where n is the total number of protons inside the Sun, and V is the total volume of the Sun, and mp is the mass of a proton, which has the following value in SI units. And then let's compute the total mass inside the shell, the spherical shell at the distance r, in the following way. Now let's go back to the original hydrostatic equilibrium equation, and let's plug what we just found into. Using this equation, we can now find an expression for the average temperature T of the Sun. We can also compute the total average number of particles by dividing the mass of the Sun by the mass of the proton, and we end up with this amount of particles. If we now plug the number in SI units we just found into the equation for the temperature, we end up with an average temperature of the Sun of approximately 2.3 million degrees Kelvin. This is, of course, an average temperature. In reality, more complex calculations which allow the temperature to vary according to a profile in the radial direction end up with a much larger temperature, which is of the order of 1.6 10 to the 7 degrees Kelvin. At the core temperature of more than 10 million degrees Kelvin, fusion reaction become possible. The main fusion reaction in the core of the Sun is the pp1 chain, which is represented here in this schematic diagram. The nuclear reaction proceeds in several steps, and the net result is the conversion of 4 protons into a helium nucleus, which is made of 2 neutrons and 2 protons. The reaction also produces neutrinos, which escape, carrying away part of the energy, and 2 positrons. The net result of the pp1 chain is the release of a total energy of approximately 26.22 mega electron volts. How long the Sun can radiate its luminosity by using this source of energy? We know that approximately 10% of the solar mass is available for hydrogen fusion. This provides an energy reservoir of delta E times the total number of protons divided by 10. We can now estimate the lifetime of the Sun by dividing this energy reservoir by the Sun luminosity. We end up with approximately 10 billion years, telling us that the present Sun is roughly halfway through its hydrogen burning phase. Let me briefly summarize what we have done so far. We have approximated the Sun as a spherical plasma which is made of electrons and protons which are in hydrostatic equilibrium. This simple assumption has allowed us estimating the Sun's central temperature from its mass and its radius. This temperature is high enough to sustain thermonuclear fusion of hydrogen. Now, in the following, let's now try to understand the origin of the solar luminosity. A hot body in local thermal equilibrium at a temperature T contains photons which possess an energy density expressed by this formula. The energy density of the photons depends on the fourth power of the local temperature. This constant, sigma s, is the so-called Stefan-Boltzmann constant, which has this value in SI units. Knowing the total volume of our body, we can compute the total radiative energy, which can be therefore expressed in the following way. Knowing the total radiative energy of the Sun, we can compute the luminosity simply by dividing the total radiative energy by the mean time t photon that a photon will take to reach the surface of the Sun. Let's now make a simple exercise and suppose that the photons are free to escape from the Sun. Let's consider a photon that is generated in the center of the Sun and that free flies to the surface of the Sun after having traveled a distance which is equal to the radius of the Sun, r0, which I recall here is approximately 7 × 10⁸ meters. The time that it will take for this photon to reach the surface of the Sun can be simply estimated in the following way. Let's now plug the real numbers to estimate this time. By making the simple assumption of the free-flying photons, a photon that is generated in the center of the Sun will take only approximately 2 seconds to reach its surface. Let's now use the previous formulas to compute the Sun luminosity. In this formula, V indicates the volume of the Sun. First, we compute the total radiative energy of the Sun, which is given by this term. By plugging the real numbers into this expression, we end up with a total radiative energy of approximately 2.9 × 10⁻³ joules. Now, if we go back to the formula for the solar luminosity, and we divide the number we have just found by the mean time that the photon will take to escape from the center to the surface of the Sun, tau photon, we end up with the value of the solar luminosity, which is approximately 1.5 × 10⁻³ watts, which is much larger than the real measured luminosity of the Sun. Where is the problem? We have assumed that a photon that is generated in the center of the Sun will free fly to the surface. However, the medium, the plasma, which the Sun is made of, is not transparent. It is opaque. Therefore, the answer is in the opacity of the medium. When a beam of photon traverses a layer of thickness ds, it will undergo a number of phenomena. It can be, for example, absorbed by the medium, or it could be scattered by the medium. The end result of this ensemble of processes is that the original intensity of the photon beam will be decreased by a certain fraction depending on the opacity of the medium. This fraction can be expressed as a function of the original intensity of the photon beam, of the local density ρ of the medium, and the opacity k of the medium, which in SI unit is measured in square meter per kilogram. This means that over a distance ds sufficiently small for k times ρ to remain constant, the number of photons is decreased by this factor here. Which are the sources of opacity in the Sun? Strictly speaking, the opacity is a function of the frequency of the electromagnetic radiation and also depends on a multitude of atomic processes. In the Sun, among the different interactions leading to opacity, the most important are the inverse Bremsstrahlung, or free-free absorption, the bound-free absorption, or photoionization, the bound-bound absorption, or photoexcitation. However, for temperature larger than 10 million degrees, the dominant process is Thomson scattering, the scattering that photons undergo over free electrons in the plasma. The Thomson scattering cross-section is linked to the classical radius of the electron, and it is extremely small, as can be seen from this formula. Using the Thomson scattering cross-section, we can compute the mean free path of photons to undergo Thomson scattering on free electrons in the Sun interior. The mean free path will depend inversely upon the local density of the plasma and the Thomson scattering cross-section. Now, if we plug the number into this formula, we realize that the mean free path for Thomson scattering, it is extremely small, of the order of a centimeter. This is much smaller than the Sun radius. And in this limit, the photons undergo many scattering before exiting the surface. We can represent this process as a diffusion process. The spreading of an ensemble of photons that undergo a diffusion process can be represented in the following way, where D is a diffusion coefficient. The diffusion coefficient can be computed as the ratio of the mean free path between two collisions divided by the effective time between these two collisions. If we use this formula, we can compute an average time that it will take for an ensemble of photons to diffuse up to the surface of the Sun in the following way. The striking result is that it will take approximately 2,500 years for a photon to escape from the center to the surface of the Sun. This reduces dramatically the luminosity. To show this, we use the formula of the luminosity we used before, and we plug the numbers we have just computed. If we do that, we obtain a value which is very close to the actual luminosity of the Sun. The second important result we can obtain is by recalling the average effective temperature of the Sun that we have estimated using the hydrostatic equilibrium hypothesis. Using the expression for the mean free path for Thomson scattering, we can find a relation between the luminosity and the mass of the star. In doing this, we realize that the luminosity scales like the third power of the mass, and this is an extremely important result, since from basic principles we have recovered a scaling law which is experimentally observed for main sequence stars. In this module, we have derived estimates of solar properties from basic principles. We have made dramatic approximations to shed light on the basic physics. We have made the assumption that the Sun is an homogeneous ball of protons and electrons which are in hydrostatic equilibrium. We have also assumed an ideal equation of state, which is that of ideal gases. We have also made the assumption that the energy is transported solely by radiation. This has allowed us to compute some of the most fundamental properties of the Sun and, in general, of main sequence stars. However, the assumptions that we have made are not entirely satisfied. For example, the Sun contains other elements than hydrogen, and also it shows some internal structures and small deviation from the ideal gas law. Furthermore, the Sun has other important elements that contribute to its dynamics. One of these elements is the presence of magnetic fields, which we will deal with in the following modules.